Hello students, this is the Laws of Logarithms Part 2 video. We're going to be looking at different techniques of solving log equations, what's the best method for that, how do you know which type of log equation you have, because there's two types we're going to discuss, and then making sure you understand that because logarithms have a domain restriction of 0 to infinity, so parentheses on both sides, we do have to check all solutions to logs. So just to remind you, the properties of logs that we learned in the part 1 video are that if you have the same base and you have two separate logs and they're connected by addition, then that becomes one single log of that base with multiplication of the two arguments. And then if it's subtraction between them, it becomes division of the first one divided by the second one's argument. And the last property we learned in the last video was that if you have an n or an exponent essentially on your argument, you can bring it to the front as a multiple or coefficient in front of the log. So the solving equations with logarithms, there are two basic types of log equations covered in this specific course. Problems can either be written as a log on each side with the same base, so log b of x equals log b of y. If you can get your equation to look like this, then your method of solving is that you set the arguments equal and you solve for the variable. If your equation has a singular term at all that does not have a log on it, so for example this y right here, then you cannot use method 1. So if you have a problem where there's a 2 or just an x and it doesn't have a log connected to it at all, then you have to get all the logs on one side, combine them down to one log using our properties, and then you have to use the definition of the logarithm to convert it to exponential form and solve from there. So essentially, when you're looking at these equations, the first thing I tell people to look for is, does every equation have a log, or each term have a log or not? If each term has a log, you're probably dealing with method 1. If there's a singular term or even more than one term that doesn't have a log, then you're going to be dealing with method 2. But in both methods, you must check all of your solutions at the end because logarithms, like we said, have a domain restriction, and each argument, which is, remember, the part inside right here of the log, that has to be greater than 0. If a single part of that fails on any of the arguments in the entire equation, then it is not a solution. Okay, so let's look at our first one here. So notice I see a log connected to each of the terms. So it looks like we're going to be able to get the case where we are going to get a log on each side. So we're going to use our properties to try to make that happen. So since I see subtraction between these two logs, and notice they're both base 10, I'm going to combine them into a division of the arguments. So this will be log of x plus 3 over x. On the other side, I see a log and a 2, but there's this 3 out front. It's still connected to the log term, but remember when we have a coefficient out front, we can put it back inside as a power. So this would become log base 10 still, 2 to the third. So I have a log base 10 on each side, 1 on each side, so then I can set the arguments equal. This is a method 1. So x plus 3 over x equals 2 to the third, which I'm going to go ahead and work out. That is 8. And then I would try to solve for x. So I'm going to think of this as 8 over 1, and I'm going to cross multiply. So this would be x plus 3 equals 8x. I would subtract over the x. So that's 7x. Divide by 7. So I think my solution is 3/7. I need to go back through and check that in each part of the arguments to see if it's still keeping my argument greater than 0. So is x plus 3 greater than 0? That's the question we need to ask. So this is my check. Well, 3/7 plus 3, those are both positive, so yes, that's going to be greater than 0. Sometimes you don't need to work it out if it's very clear to you that it's greater than 0. If I do just x being greater than 0, well, 3/7 is greater than 0 by itself, so that's also a yes. The last argument was a 2 in the original equation, so 2 is greater than 0 by itself anyways. That means that that one wasn't dependent on what the x was. So since everything works out, we're all greater than 0, this is a solution to that log equation. Okay, let's look at number 2 that I've picked out here. So this one, we have addition between the two natural logs, and notice every term has a log, so I know this is going to be probably a method 1 solving again. When we have addition between two logs that have the same base, we change it to multiplying the arguments. So this will be 3 times that negative 4 minus x. Now I like to write the monomial first, just makes it easier. And then this is natural log of 2 minus x still. I'm going to work out the inside of that. That would be negative 12 minus 3x, natural log of 2 minus x. Okay, since we have the same log on each side and 1 log each, so we set the arguments equal. And we solve for x, so I'd add 3x over. So that's going to be positive 2x once it's added over. I'm going to subtract over the 2, so that's negative 14. And then divide both sides by 2, so we get negative 7. Remember, we have to check that, though. So negative 4 minus x, we want to know, is that greater than 0? Well, negative 4 minus a negative 7, that'd be negative 4 plus 7, and that's going to be positive 3. So yes, that is greater than 0. 3 by itself is already greater than 0. That's the argument on the second log. And then 2 minus x greater than 0. 2 minus negative 7 will become 2 plus 7, which is greater than 0. So yes. So as long as it checks out in each piece of the argument, we say that it is a solution to the log equation. Okay, let's look at my third example. Now, if you notice, this is the first time I've had a term in this equation that doesn't have a log attached to it. So notice this 1 is singular there. It has no log attached to it. That means we cannot use the log equal to a log method. We have to do a log on one side equal to this part that doesn't have a log. And then we'll convert that to an exponential form. So because there's a plus sign between these, we're going to combine the two logs that have the same base. And it's going to be multiplication. So x plus 3 times x plus 5. We'll go ahead and work that out. So that's log base 3 of x squared plus 3x plus 5x plus 15 equals 1. So that's log 3 of x squared plus 8x plus 15 equals 1. Okay, so at this point, you're looking at this equation and you cannot set this equal to 1 because there is not a log on the right side. So we have to convert this to an exponential and try to solve it from there. So remember your base to the exponent, remember because the answer to a log is an exponent, so 3 to the first equals all of this. So that is x squared plus 8x plus 15. 3 to the first is just 3. Sometimes it'll be a little bit more exotic than that, like, a squared or a cube, and you'd have to work that out. So we need to then try to get this to be solved. Now that usually means we're going to have to do quadratic formula, or we're going to have to do factoring. Hopefully it'll factor for you. So if we subtract over the 3, that's going to be a positive 12. And I believe we can factor this one into x plus 6 and x plus 2. So I have two possible solutions of negative 6 and negative 2. So this is why it's crucial to do the check. I wanted you to see one where we don't get an answer, or one of our answers doesn't work. They could both not work. They could both work fine, so you have to do the check. So I'm going to do the check for each one. So I have two arguments here, x plus 3 and x plus 5. One is not an argument, it's not inside of a log. So I need x plus 3 to be greater than 0. Negative 6 plus 3 is negative 3. That is a no. As soon as one of the argument fails, this is done. X equals negative 6 is not a valid solution. Both arguments have to pass for it to work. And then for negative 2, we'll start again. So x plus 3 is greater than 0. Negative 2 plus 3 is greater than 0. That's 1. So that one's good. And then we do negative 2 plus 5 greater than 0. And that is positive 3, which is also good. So the only solution is negative 2. And then my final one for this video, we have, this one sometimes gets people because they don't notice the 2 that's right here. But there's a 2 that does not have a log connected to it by time, so therefore it's a singular term. It is not going to be the problem where we can get a log equal to a log. So if you have logs on both sides, but you have a non-log term, you need to get all the logs over together and then have it set equal to the 2. So to get that log to move over to the other side, we're going to subtract it over, since it's a positive log on that side. And then since this is subtraction and same base, we'll write this as a division problem. And again, you cannot set this equal to 2 because there's not a log on the right side. You have to do the spiraling technique, which is what I call it, of converting the log to an exponential. So this would be 4 squared equals x minus 5 over x. That's 16 equals x minus 5 over x. Multiply both sides by x, or cross multiply if you want to think of it that way. Subtract the x over, so that's going to be 15x equals negative 5. So this is going to be negative 5 over 15, or negative 1/3. Now we need to check that. So I have two different arguments to check that in. So x minus 5 greater than 0, negative 1/3 minus 5 is not greater than 0. So it fails. It's also, by itself, x greater than 0 would have failed. Either one would have failed. But remember, it only takes one for it to fail and not be a solution. So this whole equation is no solution because the only solution we got didn't work. All right, I hope you enjoyed this video, and hopefully this will help clear up how to know which way to solve your log equation.